Can you hear me now? Can you hear me now? Can you hear me now? I've got volume showing there. I'm not getting it here. I've got volume here. Let's try this now. All right, I've got that going. And let's see. Stream is coming back up. Can you hear me now? All right. There we go, there we go. Here we go, there we go. I'm just repeating. Testing, 1, 2, 3. 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 Can you hear me? I've got audio on my audio mixer, and I've got audio showing on the YouTube channel side. I just need confirmation that you can hear me. Check your... I have audio here. I also have it on a test browser. Test that out here. All right, let's try this. Yep. All right. So I am now hearing this on multiple sources. I just went to another computer, pulled up the stream, and I am hearing the audio come out. So I'm hoping this will catch up with you guys. All right, so I'm definitely seeing audio streams everywhere, so I'm going to start all over again. um, I am going to repeat a few minutes of chit chat here. All right, so we're going to be talking about chemistry. Now, chemistry is built out from the idea of physics. And the ideas that we're going to be looking at have to do with how the electric charges of protons and electrons gather together. And these are things we build up to in physics in general. Our idea for this is well, the laws of physics describe how everything works, but when we get a collection of a lot of particles together, their combined properties have a group behavior. And so the group behavior we're first going to look at is what makes up atoms and elements. And these come from the quantum mechanics of how you get a certain amount of protons together and what they do with the electrons and how they bind and work together to pull all this stuff together. And so chemistry is the idea of that collective physics of group behavior of particles. and specifically protons are the driving things. These heavier, one charge, positive things that make up the nucleus. And when we gather large quantities of them together, being held together by nuclear forces, making a nucleus, electrons gather around them, which are negative charge things. And so we have these very heavy, dense, positive thing with a cloud of negative charges on them. And it's the interaction of that cloud of charges that really describes what we're going to be doing with chemistry. What we're doing is classifying how we view things and how we predict things. We're not even going any further than what we did with M&Ms. We worked our way on, we have a reality, and we start going, well, that thing over there, I'm going to call it blah. And everything that looks like blah, I'm going to call blah. And we find patterns with blah. We are now not looking at matter as a collection of energy and forces in motion. We're looking at matter as an interaction between elements. And we're going to try to figure out why carbon is different than carbon dioxide. Why carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur make living things. Why they gather together in these complex gear-like structures that make machines. And those machines are organisms and life. And so we're going to put all of these things into a cookbook of chemistry. And that cookbook of chemistry is going to determine how different interactions go together and how things work, how we live, how we breathe, what we get out of food. And a lot of it is the storage of energy. Energy is one of the big points that we'll keep coming back to. But what we want to do is we want to look at the classifications of matter that lead us to think chemically, and the behaviors that come from these atoms and elements that let us think chemically. And so all of science is we arrange things into groups. If those groups are useful for us, we look for patterns in them because we want to make predictions. We want to make predictions of things. And the book here kind of retreads a little bit and goes, hey, look, here's some fish, right? And these fish have a pinky flesh, and they migrate in different points of their life from saltwater to freshwater. We're going to call these things salmon. And salmon have these behavior. And looking at traits and characteristics of animals has been a really good way of classifying the relationships of animal. Darwin was able to find out that animals in families shared traits, and those traits changed in reaction to the environment over long scale time through genetic mutations and adaptations. And so we kind of said, hey, things that have the same traits are sort of related, and we developed a classification in biology. Later, when we found DNA and genetics, we could go back and say, well, actually these things created the same adaptations to the same environmental stimulus, but they're not related. They came from two different families or two different groupings. And so as our understanding and classifications got better, we get a better story. And so the classifications of chemistry are really, really helpful for a big part of the story of what things are. We're moving our way up from particles, protons and electrons, into groupings of particles that we're going to call atoms. And chemistry deals with groupings of atoms and how groupings of atoms work together. And so to do that, we're going to want to look at matter. Right? And matter in a more specific context than we were doing before. Our physics viewpoint of matter is it had mass, it has charge, right? Those are two properties that we gave to matter, and we calculated what mass and charge can do. And so the mass occupies space, and the charge occupies the electromagnetic field. And so what we're going to look at is that matter, we're going to start just in general. We look around, and there's metals and non-metals. Metals have lusters to them. They conduct heat very well and electricity very well, and they're malleable. You beat on them and they will change shape. They flow. They flow instead of breaking under stresses and strains. To a limit, right? There's a whole industrial series of experiments on finding out when things break under stress or strain. But in this case, we're looking at how these things flow and move under the application of force. Alright, sorry about my click mouse there. I will get one microphone near the mouse there and one microphone on the other side of the room, trying to get a balanced sound here. And 2 seconds as this mic just dropped a little bit. That's what I get for adjusting my papers near each other. Sorry about that. All right, so, and you can pull metal into a wire, which is similar to it being flowing under stress and strains. There's behavior that metal has that is different to, well, compare it to a non-metal glass, right? Glass breaks. Doesn't have this flowing property. You have to heat glass to get some of these things going through. When you heat glass, it doesn't have other properties of it. Right, brittle objects are not metals. So non-metal has no metallic luster. It's a poor conductor of heat and electricity. And when it's solid, it is brittle, so it cannot be pounded or pulled into a wire. Most matter can be classified into metals or non-metals according to its property. So notice we went from the physics viewpoint where this has mass and charge, and we're now saying, okay, there's a distinction between things with mass. And that first distinction is, are you metallic or are you non-metallic? And so you look at aluminum, and that is a metal, and it has metallic properties. You can pound it into shapes. You can make wire out of it. There are different things you can do with this material because of its metallic property. Now, we also have solids, liquids, and gases, right? So I know of a metal in liquid form like mercury. I know of non-metals in liquid form like water. And I've actually worked with metallic gases. I've made gold gas so that we could drop the gold atoms onto a surface. And so gases have no definite shape or volume. I let a gas out and the particles are moving so quickly that they spread out as far as they can, given some conditions on them. They have a very low density. Liquids flow. They have a definite volume. So but they'll take the shape of their container. And I know we went over some of this before. So they have an indefinite shape and take the shape of the container. Solids have a definite volume and a definite shape. And so these are going to be our main classifications. So we have metals and non-metals. And then, well, is it in a solid, liquid, or gas? And there becomes this thing next to that, well, at what temperature? And so if we were to put these in a fixed container, these would be the differences, right? The gas dispenses throughout the container in A. The liquid, due to gravity, falls down to a level trying to fill the container or fill its volume in the container. And the solid holds its form. Now, outside of our shape of things, we want to wonder what comprises substances. If my substance is made of one thing or many things. And that actually starts hinting at a question that some liquids are different than other liquids. Some solids are different than other solids. Some metals are different than other metals. What makes them different? What building block changes between metals? And so we have to go, well, am I using the same building block over and over and over and over again? Or am I using a combination of building blocks to make this thing? And so mixtures and pure substances look for that difference. We want to look at the building blocks that make up these larger structures that we're observing, and say, am I always, the 4x4, the 2x2 Lego block, or am I the 3x2, 2x2, right? Are these little pieces different? Do they alternate? Do they change? A mixture has unlike parts and a composition that varies from sample to sample. All right. So I'm made up of multiple things, and if I were to grab from one thing, I might get 5 of one part and 2 of another. If I grab from another, it might be a 3 and 3. Right? They're in there. I mean, the word's there. It's mixed up. It's things mixed up. A heterogeneous mixture has physically distinct parts with different properties. It has layers or sections, right? It's heterogeneous, different parts. Right? Hetero, different. And a homogeneous mixture is, well, it's stuff, and if I get down to small areas and I get different bits, but overall, I can't really say there's a difference between the top or the bottom or the middle, right? And sometimes we can say a homogeneous mixture is well mixed. The things are mixed together. I tend to think of it like you're making bread dough. And when you first start mixing, or pancake batter, right? You put in your egg, you put in your milk, you put in your oil, and you put in your flour. And when you first start mixing it up, you can see that yellow of the egg, right? It's not well mixed. And so one side of that pancake dough is yellow, and not the whole dough. And as you mix and mix, and as you get well mixed, it moves from being heterogeneous, where there are different areas where the substances are in unequal proportions, to homogeneous, where you now have a nice consistency to your batter everywhere. There's no areas where you have too much flour, and it's dry, and the yellow color moves throughout. Right? Actually, when I think about this, I think that's the image that comes to my mind the most. I tend to think of homogeneous things as being very well mixed, and making a dough is actually a good visual for this if you've done that before, because you start out with it being very heterogeneous. You have your stuff in the sections that you plopped it in the bowl, and as you mix it, there are areas where lumpier or these other properties, and as you continue to mix, it gets the same throughout. Pure substances have the same substance in them, no matter where you go. Water, it's water and water. Oxygen is O2, 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 O2. A pure substance isn't a mixture of two different building blocks, right? I mean, we should have heard water is H2O. There's two building blocks that make up water, but those H2Os are bound together, right? Where when I'm doing my pancake mix, there's no binding of the egg yolk into it. I'm mixing it through. There's some chemistry that goes on with food, but we'll get into that in more detail. All right, I'm replying to Jerry here on the chat so we can see how chats go here. All right, so what we're getting is an idea of classifications, things that we can see. Again, our job in science is to look around us and put things into little objects that have patterns so we can predict. And these future predictions will help us. Now, that doesn't mean our objects are reality, right? They're our way of processing reality, and they help us see the truth, whatever it is, a little bit better. I actually think science and these things that we describe are human creations to understand something that we can't describe fully. And so we talk about parts of it. And these parts are good for us, and they help us understand that deeper, larger thing a bit better. And we can sometimes focus on one part of it really well, and to get an understanding locally versus far away. Like looking up close and looking far away. But so in general, we're talking about matter. We're not talking about energy right now. We'll get back to the matter and energy relationship in the section on astronomy. And we're going to say, well, matter will have pure substances made up of each building block is exactly the same. And we'll have mixtures which has different building blocks in it. Now, of the pure substances, we'll have compounds that are made up of different elements. Water, salts, sugars, they have the same building blocks. But those building blocks have multiple atoms in them. But those atoms are held together by energy. So there's something cohesively holding those building blocks together. And then there's elements which are made up of one type of atom. On the other side of things are mixtures, where there's no general building block. And we're going to have homogeneous mixtures where they look the same everywhere. Metal alloys are an example of this. Where we've mixed it so well it has a consistent structure, predictable patterns. And then we have heterogeneous mixtures like sand, dirt. Right? Do you ever sit on the beach and notice that some parts of the beach have a different color of sand? Some has more white sand than the black grains in it. Some is all yellow, right? There's mixing of different dissolved crystals from rock, and that mixing leaves different patterns in different localities on it. And so these have our classifications of matter. These are not perfect classifications, and we're going to find some things that might be hard to put into a bin properly. And so we'll look at what drives these and find ways to kind of make them a little more coherent and good for us. All right. So we can notice that matter can change. It can have a physical change. And I think I will use almost always boiling water. Right? I can go into my freezer and I can take out an ice cube. I can put that ice cube in a saucepan on the stove, and I can heat it up until it's liquid. I can go and run them back and put it back in the freezer, and I get ice again. I don't lose water. I've changed the physical property of water. If it's a solid, a liquid, or a gas, I can boil it off until it's steam. But if I were to put a metal plate or a still, I could collect that steam back up and get my water back. Right? So I add this energy, but the amounts of energy I'm doing just change the state of the water. I still have water in the background. But a chemical change changes the identity of the matter. And I think a really good example of a chemical change that with water is I can actually apply a catalyst to water and separate it into oxygen and hydrogen. A catalyst and a little bit of energy, and I can separate it into the hydrogen and oxygen. That is a chemical change. I no longer have water when I do that. I have something else. When we breathe in, we take in oxygen, and our cells and the mitochondria in our cells take that oxygen and use it to do a chemical reaction to produce energy. It has to break apart sugars to do that. And the carbon in the sugars chemically react with the oxygen we're breathing in. A byproduct is energy. We use that energy to do the things we do. But the structure of that chemical reaction is CO2 comes out with that. Carbon binds with the oxygen, and so we no longer have oxygen, we have CO2. And we have a difference of breathing between CO2 and oxygen. If you breathe in CO2, you're not going to be able to chemically use it like you use oxygen. And we have changed the stuff through a chemical reaction. So chemistry is an important way of changing the properties. So compounds through chemical changes, can be made into simpler substances. So what I want to say, I'm going back here. I'm going to go back here. And on the left-hand side, let me bring my mouse over. I'm going to see, we're looking at compounds. And those compounds, as I go back here, I can make into simpler substances. But the things they are made out of have a ratio. There is a building schematic for them. And I'll go back to water because at least most of us have heard H2O. There are 2 hydrogen atoms for every oxygen atom. And so if I were to break apart my water into its base components, I would get the 2 hydrogen atoms for every oxygen. Well, hydrogen has a known mass and oxygen has a known mass. And so the mass of the hydrogen I would get would be related to this ratio. In fact, the oxygen has a weight of 16 protons, 32 grams. There's like a 1 in 16 ratio going on. But we'll look at those ratios. And so what makes up a compound is always the exact structure. And so I'll say, using water as an example, H2O, I always get 2 hydrogen atoms for 1 oxygen atom. And because hydrogen has a given weight and oxygen has a given weight, when I break water into its 2 parts, I get this fixed mass ratio. An element is a pure substance. I cannot break it into something. Now, one of the things I want to say is the physical properties of a substance change with its chemistry. When I break water into hydrogen and oxygen, I don't have a liquid anymore, right? I don't get liquid hydrogen by breaking water into hydrogen and oxygen. I get hydrogen gas and oxygen gas due to the properties of hydrogen and oxygen. When I put these compounds together, they manifest properties that might be completely different than the elements they are made of. An element is a pure substance. Without chemically changing water, if I break it down, and I get down to one water molecule, that water molecule acts like any other water molecule. And so these properties that come together from the compounds without a chemical change come through. Now that water molecule I can break down into hydrogen and oxygen, but hydrogen cannot be broken into anything else. And oxygen cannot be broken into anything else. Oxygen is not made out of other parts. If I try to break an oxygen atom, if I try to break the oxygen element, I destroy the atom. And we didn't start learning to do that until the 1930s and 40s, when we started learning about the nature of the nucleus of the atom and how we could change it. So when we look at these things, we're looking at a compound is made up of multiple elements. And I can chemically break apart those individual elements. But elements themselves, there's nothing I can do to make it something simpler. There's no key part. What we're going to end up saying is the elements are our alphabet. They are the basic building blocks we use. And we learned a little bit further down, Einstein did this in a 1905 paper, is that elements are made up of atoms, and atoms are the most basic part of the building block. People weren't sure about it. They used it as a mathematical model, but that's where everything comes from. And so an example here is they're using sugar. And by heating sugar or caramelizing it, we start breaking apart the complex carbohydrates in the sugar, and some of the carbon chars out. And so when you caramelize a sugar, you get this carbon coming out. That carbon you can't break down any further. And so on the left we have sugar as a compound. On the right we've got this caramelized sugar, and we're starting to get pure carbon coming out of it. And so we want to look at these things called the elements. We want to look at these building blocks that we're going to build all this stuff out of. We're going to try to figure out how we're going to make things, and what are the things that we make things about. And so the Greeks initially thought everything was fire, air, water, and earth. And those were the elements. Early philosophical science. And so there was this idea that fire was this thing called phlogiston. And it built all matter. And in a way, it was people were actually observing energy and the effects of energy. But they would call it fire. And as we learn what chemical reactions involve fire and how fire is created, well, I think it's forgivable that the Greeks did think fire was part of everything because they were tracking the energy that went about. And so they considered when you burned matter, you were releasing this thing from inside of it. And if you didn't burn, well, you didn't have any of this stuff. So here's just looking at the different ideas of it and how the phlogiston came into smoke. To be honest, there were some good observations here, but we have moved so far past it that I'm not going to dwell on it too much. What ended up happening is that the alchemists that were trying to convert one piece of matter into another decided that there were these other processes happening, and early chemists started doing things like choking oxygen from a flame and watching it die. And so Anton Lavoisier suggested that burning was actually a chemical combination with oxygen, and you could choke out a flame by starving it of fresh air. You would re-expose it to fresh air and it would start burning again. I think anyone with a wood stove or at a campfire might have noticed this. You blow on it, you get the flames to go higher. If you shut all your vents and flues, all your coals will go out, right? But as soon as new air comes upon it, that heat and energy is still there, the fire and the flames restart. And so it was by observing these things and doing experiments with them that we were able to say, there's this thing, we're going to call it oxygen. And oxygen reacts with wood. And that reaction creates a fire as a byproduct. And so he said, we need to do something to figure out what these things are. And now we know that there's 112 elements. I think we're actually up to 116 because we have lab created elements now that we can create because we found the pattern of the elements, and we can make artificial ones that don't last so long, though we might think there are natural places where they do. And so these naturally occurring elements kind of build up everything else. And so it was this idea of realizing that we weren't made of fire, air, water, and earth, but there was a fundamental thing. And so we tried to look for the patterns of how these fundamental things reacted with each other, and we built the elements. Now, Priestley discovered oxygen as a gas, and he was able to do a chemical reaction with mercuric oxide, right? So mercuric oxide, in the name, you can see there's an oxide in it. There's an oxygen in it that, exposing it to light, released the oxygen, which put the gas into the space around it. And so that would create a pressure. And he was able to see this change in pressure. So he knew he was creating something, and something that was a gas. And we consider this the discovery of oxygen was through Priestley, even though people were talking about the subject around. And so what I want to highlight by this idea, this experiment, is that there is a substance. By putting light on it, focusing energy on it, it forced a chemical change. That chemical change was able to be observed by seeing a gas being produced. Lavoisier heated mercury to form a mercury oxide. And then he measured how much oxygen was taken away from a jar. So notice the two things happening here. If you look at these two experiments, I take mercury oxide, I heat it, and I produce oxygen, and I can see the oxygen coming into the jar. Lavoisier took mercury and produced mercury oxide and measured the oxygen going away. So both of these experiments realized this process was somewhat reversible. You needed some type of energy to make the chemical reaction happen quicker, or quick enough that you could observe it. And so they were able to see that there was a gas that comes or goes into the mercury oxide. And so he was able to find how much mercury and how much oxygen were in the original substance by figuring out how much of the parts were there. And so here was their observation. Well, there's something that escapes this stuff when I heat it. I can make this stuff if I put it in oxygen. So that stuff escaping might be oxygen. And they were able to reverse the same process. They were able to find what two of the building blocks were. Oxygen and mercury. Now, as we developed different ways to find the pure elements, we were able to break things down, we started finding more and more of them. And so different techniques let us discover how many of the elements there were. And so we start naming these things. Those names are accepted so that we can talk across the world. There is a standard for the names. And those names usually honor the discovery or the history of the substance. And those names themselves also have internationally recognized symbols to show. I'm looking for my periodic table of the elements here as I do this. And for example, some of them have an odd history. So the compound that we get the element lead from, or not the compound, lead was discovered by the Romans, used by the Romans for plumbing. In fact, the word plumbing comes from the Roman word for lead. They used lead in their first pipes, which we now know is a bad thing to do. But they use that. So the symbol for lead is Pb from the old Roman word for lead. A similar thing happens for iron. Iron is a recognized element, and that word is ferrous. You'll even see we will talk about ferrous materials, meaning they rust. Because there's an iron nature to them, and that comes from the old Latin. Latin gets infused in a lot of these, mainly because Latin was the language of education when a lot of these things were being discovered. Some of the what is gold has the symbol Au for or, the Latin word for gold. I'm trying to think of some. Well, hydrogen just has the symbol H for hydrogen. Helium has the symbol He for helium. And so there's recognized symbols and recognized names. And a lot of the times, some of the symbols are a little bit hard to sometimes get with their name. For example, potassium has the letter K as its symbol. But those all exist in a periodic table of the elements. And I kind of want to get what happens with these substances. So as we discover these substances, we have to figure out what they are. And we try to figure them out from their properties or what they do. So for example, helium was named because it was first discovered by seeing the pattern of its electrons in light from the sun. And the old Greek word for the god of the sun was Helios. So they named it helium. And we have named some after places or cities. Some of the artificial ones, there's berkelium, named after the University of Berkeley, California. There's Einsteinium, named after Einstein. And we use Greek mythology a lot. And so all of these things come together. Now, Dalton used these symbols for the elements. Hydrogen, oxygen, carbon, nitrogen, sulfur, mercury, gold, zinc, lead, silver. He thought water was an element. Water is very hard to break down. I'm sorry, he's doing water as being hydrogen and oxygen. I apologize. And sulfuric acid, where you can see that he has oxygen, and sulfur. And so he was starting to build an idea of chemistry using these symbols. But it was a very unwieldy system because it didn't say anything about the elements. Now, if we look at what everything is made of, we have some elements that appear over and over and over again. Iron, oxygen, and silicon make up 88% of the Earth's solid surface. In fact, most of the Earth is silicon oxide. All the oxygen you breathe was actually trapped in rock at one point in time. We look at the geological record of the Earth. There was a time when there was very little oxygen in the atmosphere. Volcanic processes release some of it in gaseous form, but the actual oxygen you breathe really came or got liberated from being trapped in silicon, and we'll see why it's trapped in silicon a little bit later, from bacteria. There were bacteria that ate the silicon oxide rock and pooped out oxygen. And they did that in such large quantities that they started flooding the air with oxygen. So the type of biology that exists now couldn't exist early on the Earth. It took organisms to radically alter the Earth. And there are many periods in geological history where the raw elements of the Earth get disrupted by the organisms on them, and they the proportions change. There was a period where plant-based life was so large, and there were still these bacteria producing oxygen from the rocks, that the oxygen saturation in the atmosphere was more than it was here, because plants take carbon dioxide and spit out oxygen. And so they're grabbing this carbon dioxide from volcanic outgassing. The chemistry inside of the plants are spitting out oxygen. And there are beautiful examples in the geological history of dragonflies that are about 2.5, 3 feet long, like 6 foot wingspans. Those dragonflies are genetically the same as the dragonflies now. But because insects breathe through their skin, if there's more oxygen in the atmosphere, they can get much larger than they are now. The only limiting factor to how large an insect grows is its ability to process oxygen. And they've done experiments where they'll put ants in a higher density oxygen aquarium or ant farm, and they just get larger. And so we're trying to figure out this record. So most of the solid stuff is iron, oxygen, and silicon. And we will see why it's mostly these things. And I read these elements now, and I can say, hey, I know what a star does to make those things. And then in the air itself is nitrogen, oxygen, and hydrogen. You are made up of mostly hydrogen, oxygen, and carbon in some combination. And so there's really only about 6 or 7 things that make up most everything. All right, so before we get into the chemical symbols, I want you actually to think about something that shows why chemical processes are important. I'm actually going to do it on the blank screen here, I think. I have a young tree. It's got its roots into the ground. Now that tree's going to grow and get much bigger. Where does the stuff come from to make the tree bigger? And I hope that because I'm talking about chemistry, well, there's going to be some chemistry involved, right? There's some chemical reactions. But we still need stuff to make the tree bigger. It doesn't magic mass out of nowhere. It has to take mass from somewhere and build it into a tree structure. So this is the awkward pause. Think about it. And I'm going to give you some answers that people give sometimes. The one that some people will say is it comes from the ground, right? It pulls this stuff out of the ground and it gets bigger. And it does get nutrients from the ground. Specifically, it needs carbon. So, well, I'll even put it in. It mostly needs carbon because a tree is mainly carbon, right? And hydrogen and oxygen. But the ground, it's really pulling up nitrogens and these small minerals that help it chemically process. But if it got all of its stuff from the ground would have to lose stuff. And trees would create really big holes underneath them. And they don't. Well, does it get it from the water? Well, water would be has no source of carbon. It's hydrogen and oxygen. So there would need to be carbon in the water. And so what trees do is they take CO2 from the air and they process it through photosynthesis and they spit out oxygen. And the carbon that's left behind, they build into their structures. So trees don't actually grow up from the ground. They're anchored in the ground. They're actually crystallizing out of the air. They're grabbing carbon out of the air, chemically processing it through a chemical process, and turning it into the structure of a tree. So trees grow more like a crystal, right? Their chemistry is reacting with the chemistry that they're soaked in. The ground is the thing that they're anchored in. And they do some things to process stuff in the ground. But mostly a tree is getting its stuff from the air. And it's getting its stuff from the chemistry of the air. And so we want to kind of want to think about these chemistries we're looking at, because these chemistries will do many things for us, and especially drive a lot of the biological processes. All right, so we're going to go back. We're going to classify things. So yeah, there's only about 6 elements that make up everything, but some of those processes are amazing. You know, trees grabbing CO2 from the air, spitting back O2 and ozone. And so the more trees we have, the more oxygen we have in the air. The more people we have, the more CO2 we have in the air. So there's balancing factors that we have to do if we want to not change our atmosphere a lot. And we know our atmosphere has changed a lot in the past from what we can see in geological records. But how do we classify this stuff? So there are about a dozen elements that have single capitalized letters for their symbols. The rest have two letters, with the first capitalized and the second lowercase. And as I said, they come from their Latin names. So I'm going to pull one up here. Involves me switching screens here. I apologize for that. I have a periodic table. I want to make sure it can come up here. Where is G periodic? There we go. All right. I'm going to pull up my periodic table here. Give me 1 second. All right. So this is the periodic table of the elements. And this shows us the different elements. Now there is a pattern, and we're going to learn why it is within this pattern. But here's what we mean by the symbols. So H for hydrogen, and let me see if that pulls up. And H for hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And there's going to be a pattern where how all of these are related. So I'll come back and forth to this periodic table. But notice that we have no more than 2 letters and a capital and a lowercase. There are some that get single letters because of their importance. Iodine with the single I, or oxygen with the single O. And so that's what we're trying to describe there, is how we name these things. Let me see if I can get back to my slide here. Sorry, switching screens is a little slow there. All right, so we want to talk about the structure of the atoms and the symbols and how we're going to try to use all of these things together. So if we have a molecule, it's composed of 2 or more atoms held together by a chemical bond. Some chemical property is going to bind these things together. And so a molecule is 2 or more atoms held by a chemical bond. An isotope are the same element but different masses because it's got some extra neutrons in it. And so the atomic mass is the average of all of the mass of an isotope. And I think I'll try to use a thing you might have heard of before, and it's called heavy water. It's water that's hydrogen and oxygen. But one of the hydrogen atoms is deuterium. It's got an extra neutron in it, so it's slightly heavier than a normal hydrogen atom. Chemically, it acts like water. Has all the chemical properties of water. But because it's slightly heavier, because it has this extra neutron, it has some different nuclear and energy properties. And so when we're dealing with chemistry, some of the isotopes come into play, but in general, molecules and elements. Now, Dalton fixed the mass ratios of atoms. He measured different things, and he figured that the weight of hydrogen was 1. Hydrogen was the base. If I pull back up here to the periodic table of the elements, let me see if I can get it back here. Where did I put it? Nope. I put it here. Sorry. So I go back to the periodic table of the elements. Let me get all of that on the screen here. There we go. I go back to hydrogen's up top at 1. And up in the upper left corner is the lightest, and we move left to right. This is the next heaviest, and so on. And we get heavier until we get down to the heaviest things here. And the heaviest things here. So Dalton did a really good job of figuring out where the mass itself was going to be coming from. He just didn't know, not where the mass is coming from, what the mass ratios were. And he was able to organize the matter based off of what he could figure out by doing chemical reactions. And so Dalton started finding, hey, these things weigh more than each other. Now, I don't know what it's made of, but I know their mass ratios. And so he's able to start figuring out their weight. And so the mass of an element, we had to come up with something to compare off of. And so what we decided to compare off of was a particular abundant isotope of carbon. We needed something, we went with carbon-12. And so a carbon-12 has an atomic mass of 12 grams. And 12 is going to be 1 atomic mass unit. We just said we're going to pick this isotope, and 12 grams of it will be one atomic mass unit. The number of protons and neutrons that make up an atom determine its mass number. And the reason for this is electrons are so light that they don't really affect what we can measure. They are whole numbers. We don't use fractions or decimals for the mass numbers. So if I come back here, I'm trying to pull this up. Well, it's not showing on there. Let's see. We've got our whole number. Sorry, I switched off to get my periodic table off. Atomic numbers are whole numbers. Mass numbers are whole numbers. The atomic mass is not. And so because the atomic mass takes into account any isotopes, it rounds to being decimals. So we will talk mainly in atomic mass numbers. Now I'm going to skip this. It's how we can measure elements. What I want to do is get into the periodic law. And I'm going to end this first kind of hour with talking about the periodic law. And what happened was Dmitry Mendeleev gave us a scheme to classify elements. He was looking at elements, trying to figure out why they kept doing the same things over and over again. Why the elements kept having similar properties, or why certain chemical reactions you could replace the compound with another compound. So if you had a chemical reaction that was using chlorine, you could replace it with fluorine, and you would get a chemical reaction. It would not be the same substances, but they would react in similar ratios. And he was trying to figure out why these things happened, and also why certain things had similar properties. Why, if you looked at a metal, another metal had similar properties. And he started to try to organize things. And this classification scheme that he invented really made chemistry work. And it was based on the chemical properties of each element. And you notice that they increased in a periodic manner. That every so many elements by its mass, you would get a similar set of properties. And what he did was he used a table to predict for elements that hadn't been discovered yet. And I think that was the good observation, as you noticed, as we start getting more heavier and heavier elements, every 8 I start seeing the same pattern. Every 8 I start seeing the same pattern. Every 2 I see this pattern. Hey, I have something that should be here at this 8, but I don't have something there. We'll eventually find an element there. And it's when we started finding the holes in his periodic table, we knew that he was on to something. And he left blank spaces in there for those elements. And so I'll see if I can get this to switch back to the periodic table. There we go. So notice that there are columns, distinct columns. There's some gaps up here. All right, there are some gaps here. And then there are distinct columns. And that's what he meant by periodicity. That every so often, and so everything in a column has similar chemical properties. So, and then when I was talking about fluorine and chlorine having similar chemical properties, it's because they're above each other on the periodic table. These column here, these gases are very inert. These noble gases won't react with other gases. That was a behavior that was noticed. These elements have a tendency to form compounds with these elements. And these have a tendency to work with these. And so these columns, these up and down columns of data had meaning. And these gaps in here, we will find out, have meaning too. We're going to find out what causes these columns to have patterns of properties. But it was just recognizing that we could classify things by similarities that helped us discover what was going on. And so the periodic law, similar physical and chemical properties reoccur periodically when the elements are listed in the order of increasing atomic number. And so the modern periodic table comes from that. It's made up of rows of elements and columns. Each element is identified by its chemical symbol, and the number above the symbol is its atomic number. The number below the symbol is its atomic weight. A row is called a period, and a column is called a family. So the period is how often until you repeat chemical properties. So within a period, you should not see a repetition of the same chemical properties. Families share traits. So within a family, you should see traits. So let me again flip over to my periodic table here. And so we have, notice the color coding within certain families, and then our periods go across. Notice up above, there is the atomic number and the atomic weight. So, and here the book breaks down one, and it shows period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Notice there's a little breakout in period 6 and 7. Those elements down here in this part of it that have the little lines breaking out of them, they would have properties that fall within here. Right, you see how these lines wedge all of this back into here? And we'll discuss why that exists. But the important thing really is in the basis of these 7 periods and the properties of the families, the major families. So the chemical behavior of elements is determined by the electrons in the atom. And so if you want to think about an atom as being a nucleus and electrons, so we have this big, whoops, it doesn't undo, so let me erase that. We have our nucleus, and then we have electrons on the outside. The space between the nucleus and the electron is large. The scaling factor that I used before, if you take a tennis ball, sit it on the 50-yard line of a football stadium, and you go and sit in the nosebleeds, and you take the period from your textbook and hold it up, that would be the nucleus, and the period would be the electron. But the electron has just as much electrical charge as the nucleus. And so they're attracted to each other by their different charge, but other atoms are only going to see the electrons. There's so much empty space, they're only going to interact with the electrons. And so the electrons drive how atoms see each other. And so energy levels are quantized to talk about layers of electrons. And that's what we noticed with light. Light came in distinct quanta, and we could move an electron up or down an energy level. And it's that motion of energy and the energy levels that help the chemistry work. A shell are electrons that have the same n values, which is a base energy level. Each n is a row in the periodic table. And so what ends up happening is the electrons in the outer shell correspond to the period in the periodic table. So n determines how much energy levels you're at, what energy levels you can have, and the number of energy levels you have determine your outer shell. Again, the Shrek idea, it's like onions, there's layers, and it's your outer layer is the first thing you have to go through to make things work. And so each period gets an extra outer layer. So the hydrogen atom only has one outer layer. The helium atom only has one outer layer. That's why they share a period. Now, what ends up happening in quantum mechanics says, hey, you know what? If you have n equals 1, you can only have 2 electrons in your shell. And that's why there's only 2 atoms in the first period, because the hydrogen has 1 electron and the helium has 2. And that's the difference between the atoms, is the number of electrons in the outer shell. And so each period ends when you completely fill that outer shell. Each family says how many things you have in your outer shell. And the outer shells are that barrier that determines how all of chemistry is going to work. And so let's look at our chemical families. So I'm going to have to go back and forth between the period here. Sorry, I skipped over one thing here. I'm going to come back to it. So if you look at these groupings on the periodic table, and we look at how the period moves about, we have some groupings or colorations of families that come together, and some ideas that we pull across. And so the ability for the shells to lose electrons changes from the lower corner to the upper corner. And your textbook has a beautiful diagram for this that I wasn't able to find to put into the slide. It's on page 373 of the physical textbook, that shows the electronegativity of it and how much energy is. And so it's very, very easy for electrons to be lost down here. Very hard for electrons to be lost here. And there's this ability for these outer shells to move electrons and share electrons that moves diagonally across these periods. But let's look at how all the families come together. So we have things that call alkali metals, and they're the first one. They react well within water, right? And you get the idea of alkali batteries, and they're 1A, the first grouping. Group 2A are the alkali earth metals, because they're not as reactive with water as 1A. Not saying that they're not, but they are. And then we go all the way over to group 7A, which are halogens. And so 1A, 2A, and halogens. And halogens need only 1 electron to fill their outer shell. And they're not completely filled. And so they're very reactive, because they're I guess if you want to think of what chemistry is trying to do, everything is trying to fill its outer shell. And if you only need 1 electron to fill your outer shell, and every outer shell has electrons in it, you're going to be going, hey, I'll take yours. Hey, I'll take yours. I can work with you. And so they end up being very reactive. The very last grouping, which I said are inert, back down here, are noble gases. That's the helium, neon, argon. What is the name of that? See, I don't know. The names always give me. Is that krypton? Yeah, it's krypton. Xeon and radon. And oganesson. Oganesson is synthetic. These gray ones are only made in a laboratory. So helium, neon, argon, krypton, xeon, and radon are our noble gases. And they have completely filled their outer shells. So they don't need electrons. and they're holding on to them rather tightly, they tend not to react with anything. And notice that how look at that the difference of one electron in the outer shell changes it from I don't want to react at all. It's really hard to get xenon or neon to react with things. It doesn't want to react chemically. But then you look at our halogens and they want to react. And that's the difference of one electron in the outer shell. So these properties of chemistry coming from how the electrons fill the shell around the atoms, but they're very subtle. A difference of one electron makes extremely uniquely different chemical families. And so here it puts them on the periodic table, but I pointed them out on the larger periodic table. And you want to think of these are the ends, because the ends of the period, when I'm in 1A, I have one extra electron. When I'm in 2A, I have two extra electrons. I shouldn't say extra. I have one electron in my outer shell, and I have two electrons in my outer shell in 2A. When I'm on the other side, when I'm in 7, I have 7 electrons in the outer shell. And when I'm in 8, I have 8 electrons in the outer shell. And the general rule is the outer shell is 8 electrons at the most. And there's some subtlety to that. But it works for chemistry that for any period above 3, there are 8 electrons in the outer shell. And so the things that we react with the most either have 1 or 2 spare spaces or 1 or 2 extra electrons. The things that don't react at all have that outer shell filled. And then the stuff in the middle kind of, well, it's in the middle. It can be a little bit of both. And so the ends get these really big descriptions because we get a lot of chemical reactions from the ends. Now, we have metals, nonmetals, and semiconductors. And that has to do with the outer electrons. The outer shell electrons are represented in what we're going to call dot diagrams. It's the best way of showing this. And so the noble gases have completely filled their outer shells and are stable. All other elements react so as to fill their outer shell and become more stable. This is everything I just said, right? I'm putting it up in bullet points now. Sorry, I have a habit of, like, the previous idea leads me into the next idea, and on certain slides I'll go, yeah, that's everything I just said. Right? This is what we just said. I haven't talked about the dot diagrams yet, but here are what the dot diagrams look like. And so notice, in the 1A column, what I said in words is represented by the dot. Hydrogen has 1 electron in its outer shell. You pop over onto the far right there, and helium has 2 electrons in its outer shell. And so we have these outer shells. Now notice in the middle here, if these can have 8, well, I could take 5, or I could give away my 3. And what every atom wants to have happen is it wants its outer shell filled. And so one of the first things an atom can do is it can lose an electron. Physically lose it. If it loses the electron, it loses its negative charge thing. And it becomes a positively charged thing. And it's going to become a positive ion. Right? And if it gains an electron, if it grabs one from somewhere else, it gains a negatively charged thing, and it becomes a negatively charged ion. And ions form one of the more basic parts of chemistry, dealing with charges, because charges are attractive and repulsive. That attractive and repulsive nature of ions can cause them to pull together, to bond, or called ionic bonds. And so the electric charge of the outer shell goes. Now, if we lose an electron, we make ourselves an ion, a positive ion. If we gain an electron, we make ourselves an ion, and we are a negative ion. Now, ions are probably the more abundant and easier to understand chemistry, and they happen a lot in moving energetics about. Ionic solutions, you put salt into water and you get the sodium and the chlorine coming out, and you have ionic solutions that have charge that'll come back together. Very, very common, very fundamental for how things happen. We can also ionize outside of the chemistry by throwing energy at it. When we were making light, if we put too much energy into an atom, we could kick its electrons away and we could ionize it. And so energizing things are ions. We go back to our flame, and the reason we're seeing light from a flame is so much energy is coursing out of the chemical reaction that it's causing the gases to lose their electrons. And so we're actually seeing a plasma of ionized gas at the end of a candle. Ions really drive a lot of things, and it's, hey, am I gaining or losing an electron? Cations have lost an electron, and it's a positive charge. Anions have gained an electron, and they're a negative charge. My son just told me the other day, I'm not good at mnemonics, but he had a good one. Anion, a negative ion. I like that. Ions gain or lose an electron, and if you want a negative charge, a negative ion, anion works well. And then cats. Everyone likes cats. That's a positive ion. Elements with small numbers of electrons in their shell tend to lose electrons. All right? They say they tend to, and I want to go back to the dot diagrams here. Sorry. It's easier for this to lose one electron than to gain another. Well, actually, look at it from the idea of sodium. It's easier for sodium to lose an electron than to gain 7. Right? If it's the act of moving something, right? It's easier for me to move one thing away than to move 7 things towards me. And that's what this is saying. Elements with 1 or 2 or 3 electrons in their outer shell tend to lose them other than filling them. And metals will always tend to lose electrons. Electrons with 5 to 7 electrons in their outer shell tend to gain electrons. And these are nonmetals. Semiconductors, well, are the things in the middle, right? 1, 2, 3, 5, and 7. Well, we're missing the 4s. And so our metals are everything in blue. Our nonmetals are the things in that greenish hue. And our semiconductors are this orangish hue. And notice the semiconductors are a diagonal because there are some properties of the electron shells that change. Coming through here. As things get heavier, the electron shells get further away from the central of the atom, and it's easier to lose. That's what makes that diagonal line there. As these get heavier, you get more outer shells. The more outer shells you have, the further away the outer shell is away from its protons, it's easier to lose. And that causes that little diagonal thing to happen around the semiconductors and the metals. All right. And so metals lose their outer electron to acquire a noble gas structure. Because once you've lost your electron, you look like a noble gas. Nonmetals gain to acquire an outer noble gas structure. But because they have charge, they will hold themselves together. And here's the periodic table. All right, that is the first part of chemistry. What I'm going to do here is we're going to take a half-hour break, and I'm going to record the second part of this. Now that I got the sound working, I apologize for the sound. I'll edit this out. We'll take about a half-hour lunch break. At 2 o'clock, we'll come back in, and I'll do the second part of the lecture. So this ends up being like a class, and this will tie together everything with the reading. I'll also put up the new reading on Pearson tonight, and that will get us through the astronomy section, which ends kind of the stuff we do. and I will do these last few lectures in the next 4 weeks of this, with all of our rubric stuff being the 2 sets of essays you have to write on Blackboard and the stuff in Pearson. So what I'm going to do here is I'm going to end the stream, and then I'm going to send out a link for a new one to do the second half of it. This way YouTube saves them as 2 recorded videos. But these videos will be stored, so if you want to go back for them, you can look at them. See you at 2.